First of all, I'm very grateful to Adrian Constantine for inviting me to come to this interesting meeting. You see the topic of my talk, which is on the harnessing of wave power in open seas. This is a joint work with two talented young collaborators. A lady named Dr. Dali Chu, who is now a lecturer in one of Shanghai universities, and Dr. Raphael Stuhlmeier, who is with us here in the audience, and very soon will be a lecturer in Plymouth in mathematics. But this work was done in an engineering department, the Faculty of Civil and Environmental Engineering at the Technion, sponsored by the Israeli Science Foundation. I usually like to talk on my most recent work because I don't remember so good the previous work, and unfortunately this work is completely on linear waves. So I have to apologize for, but some people say be wise, linearize, although I know also other sayings the opposite direction. Now, aim of this talk. Let's start with this. The industry which looks at harvesting waves nowadays, most of the capture of the energy is close to the coastline for understandable reasons. The aim of this talk is to give some information. Why will it be wise in the future to go out to the open sea and to see what are the problems, what are the mechanisms that we have to think about. So we want to assess the available power potential in the deep seas, introduce a self-reacting wave energy converter. It will be a model made out of two cylinders. It has to be self-reacted if the bottom is very far down. If the bottom is a few kilometers down, you want some other solution. We examined the size of these designs, and will develop a framework for wave power absorption by large arrays of this particular design. Some numbers for orientation. Most of us have no feeling for such large numbers, so they should compare with each other. The present overall power consumption is this large number. So something like 1.5 to 10 to the power 17 watt globally for all the things that we are doing as human beings. Now, the wind transfers energy into the wave motion at a rate globally over all surfaces of the ocean. If you assess this value by a number which is comparable in size, maybe 3 times larger. This is the total energy which the wind pumps into the ocean, mainly by the form of waves. But which was quite surprising to me, that the greatest part of this energy, the estimate is about 96%, is lost due to wave breaking on the open ocean, and eventually goes into turbulence, into heat and whatever. But only 4% of this large number actually reaches our beaches. So if you take all the beaches globally, then the average, then the power that reaches these beaches is of the order, is of, let's say 4 times or something like this smaller than the energy that, if you take whatever comes to all our beaches, even if you're clever enough and we can catch it, this will not supply our hunger for energy. And we definitely cannot catch everything because most of the beaches have other purposes. Our catching devices are not so sophisticated enough to catch everything. So it looks that if you compare this number with this number, that's not a big deal to go into the wave energy business. Maybe we should look elsewhere. It's not going to save a humanity in some way, but there is a potential that if you go with your devices up into the open, out into the open ocean, you can catch some of the energy. But by this, the wave height is reduced. Then afterwards, the wind pumps more energy into the waves and they grow again. So you can catch the energy a few times instead of most of it being lost by breaking. So I will now try to convey to you this idea in a more organized, let's say, mathematical way, if you want. Since not all the audience is familiar with wave generation by the wind and so on, I'll just give a few very simple definitions. And I apologize for those who already know that. What is called a fetch limited wave growth. If we have here land, and here is the water, and we have wind coming from the land over the water. What is wind? We usually refer to the average wind speed at a height of 10 meters above the sea level or above the ground. This is because wind goes logarithmically, so you have to define this. And what the waves start growing, and of course, the further you go out into the sea, the further the fetch, which is the distance of blowing of the air over the water, is growing, the wave will grow. The truth is that they don't grow without limit. They grow until some saturation is reached, because there is a balance between the energy pumped in by the wind and the energy lost due to breaking. At some distance, at some fetch, will reach what people call a fully developed sea. This is what the wind can give, and all the rest what she puts in will be lost. Characterizing the fetch limited wave growth, we look on wind of constant magnitude, and we find the distance of blowing of air over water by x, and that's our we call it fetch. Now there are many models. I don't want to confuse you too much. But there is a certain theory which is a mixture of theory and experimental evidence and engineering approaches and so on. In this respect, I would like to talk what do we know very briefly about fetch limited wave growth. And I represented in terms of a well-known spectrum, which is known to engineers and people who work in the ocean, called the Johnson spectrum. We have three-dimensional variables. One is the spectral energy. The other one is the frequency in the spectrum with waves with different frequencies, and the next one is the non-dimensional fetch. All these quantities I made non-dimensional on the basis of U10, of rho where you need it, and of G, which is gravity. This is quite a complicated equation, but it appears in it's quite standard in books, which gives the spectrum as it develops from the coast with the fetch. All the parameters here are fetch dependent, with quite complicated empirical relations. We don't have to absorb all that. There's also besides the frequency spread, there's also spread in direction of the waves. This is given by that parameter d, which is also a known function, and so this is all well known. As I mentioned, at a certain flow distance, the sea becomes fully developed, and when this happens, the gamma here turns to 1, and the Johnson spectrum becomes to a quite simpler spectrum. It's called the Pearson-Moskowitz spectrum, which goes tens of years back. So the dimensional fetch for which the sea becomes fully developed, and beyond which the energy that is transferred from the wind to the wave is completely lost due to breaking, is now a known number. This is the non-dimensional number, and it's a non-dimensional value. Of course, we'll also need in the theory that we are trying to develop, we'll also need, after we reached our WEC, our wave energy collectors, and it takes out part of the energy, the wind will continue to grow, and we need some theory for the growth of the waves by the wind, and we are here using quite standard for people working in wave forecasting, the Miles growth mechanism in its simplified form as given by Planck already many years ago. Most wave forecasting models will use a model like this, and then one can calculate the energy which is input, the growth of energy with fetch by this simple differential equation, and it of course depends on the frequency of the mode in which you are looking. Now, let's try to look on a more global picture. We have an ocean basin, and for simplicity, we take a rectangular basin. In particular, our wind blows from left to right along this basin. It can be part of the Mediterranean Sea, but it can be part of an ocean. Doesn't really matter. This is the length of, okay, so we have a schematic geometry of an ocean basin with length L, which I don't say what it is now, but later we'll use a couple of thousands of kilometers as a way for this basin. In this basin, we have a number of wave farms. Wave farms are places which have many wave collectors. We give a better picture later. The wave farms here are given by the shaded areas. So you have a wave farm, and then you have many additional wave farms all the way let's say, to the beach on the other side. Something like this. Schematic geometry shows a basin length L with a number of waveforms given by the shaded area. These waveforms are some distance delta D apart, a few tens of kilometers. We'll have to discuss what this must be. A constant wind is blowing from left, and we have some, and x0, F is in Hebrew, x0 indicates the leading fetch prior to the first device or to the first farm. We have some okay, while FD is the fetch needed for fully developed C. So we'll put the first farm at a distance which is at least that of a fully developed C, and then the waveform will take out a significant part of the energy, but not all. And the energy which will come out on the other side of the farm will again be affected by the wind and will grow. And it will grow, we would like it to go almost again to the fully developed condition. There we put the second farm, and this way it's of course a simplified picture. We'll have a series of farms all the way like this. So we have another quantity here, delta. Delta is the width of the farm. The farm will include many collectors, and will have, of course, also a certain width, a few kilometers in width and so on, with many wave collectors. Sorry about that. How do I go back? Okay, we were here. Sorry about that again. What I wanted to point out, the capital B, which is the width of that rectangular area, B is the harvesting breadth, how wide or how broad our farms, orthogonal to the main wind direction. If we want to think about it as 2,000 kilometers, this may be 100 kilometers, 200 kilometers, depending on the particular problem. First, we will do a very simple exercise, which we call an ideal wave power harvester. What is an ideal harvester? This is some magical system, which absorbs all the energy that reaches that system. It's ideal because we would like to have a thing like this. It's also ideal because we can never have a but we can think and play just and play with it a little bit. So later we'll relax this, but this is a way of introducing you into the topic. So we also give here for unidirectional waves the definition of energy flux in a wave field, which will the integral of the energy density times the group velocity over the frequencies which are in the spectrum. And here the table gives us some practical information. The fetch needed for full development, and the total fluxes as a function of wave speed. So we know what we are talking about. We took three different wind speeds. This is in meter per second. You have to multiply it about 2 to get it in knots, if you feel safer in knots. 7.5, 10, and 12.5. Our design one will be 10. We had to choose some design quantity to get things to get numbers, and we'll have somewhat and to see how the design will act in smaller winds and in larger winds. We also have looked at extreme strong winds and survivability conditions, but I doubt that we will get there. It's only also in the talk, but it's kind of if we have time. Just to give you a feeling, what is actually FD for a fully developed sea? For 10 meters per second, like about 20 knots, you need about 350 kilometers to get your sea to be fully developed. The energy flux per meter perpendicular to X, to which the main wind blows, is about 20 kilowatt per meter for this kind of fully developed wave. Just to give you a feeling how stormy this is, it's not terribly stormy. It's about a 2.5 meter significant wave height and has a T peak of close to 8 seconds. Just if people want to get feelings and not just I was brought up the way that I need to get the numbers, otherwise I don't know what I'm talking about. So let's talk about our area is 2,000 kilo. If I go back to the previous picture, which I won't do, but L is about 2,000 kilometers. That's our choice. The FD will be 350 kilometers. After 350 kilometers, we install the first line or the first wave farm. Since it is an ideal absorber and it takes up all the energy, the distance between the farms, gamma will also be FD. So again, 350 kilometers for this ideal sync between each farm. And this will leave us with some X naught, which will be larger than, which will be 597 kilometers. If I try to summarize what this means, it's as follows. Ideal harvester in a 2,000 kilometer basin with wind growth or regrowth gives us the total capture. The total capture is about 100 kilowatt per meter width, compared to about 20 kilowatts per meter width if you would only have the capture at the beach. If you let the wind blow and you put only capture at the beach, this is in theory what you can capture. So let me just read it to make it clear. Total energy flux captured by 5 perfect you mean ideal, yeah? By 5 perfect wave absorbers, or wave absorbing farms if you want, spaced at a distance of 350 kilometers from each other, over an ocean basin which is 2 kilometers long. And you see that you can, even with this extremely simplified picture, show that you can catch 5 as much as you could have. But if you go to a more refined theory, as you have to, you'll see that these numbers go significantly. Now, at this point, I have to say, what do I mean by a farm? The farm was the shaded area. But this is if you look from very far away. If you look closer, what is a farm? So what is the farm that we had that we envisioned? Definition sketch of a farm structured as a strip array of twin cylinder. This I have to explain. It will become the next slide, I think. A vision for future open sea wave power farms. So what you see here, this picture stretches very far to the left and very far to the right. That's the strip, which was in the picture like this. I'm now looking at it like this. No, I'm sorry. This is the wave farm. the farm. The width of the farm in this the width of the farm here is about 12 kilometers. I should explain what is the origin of this number, and it stretches all over B. Okay, let's read. I make less mistakes. Schematic picture of part of the wave farm as a rectangular array of twin cylinders or other types of converters, if you like. The spacing between the converters is about half a kilometer. The spacing is about half a kilometer between the converters. You can put it more or a bit less, but that's a reasonable order of magnitude. And the farm here is 25 lines. We have to discuss where this number comes from, but we'll do it later. 25 lines deep, half a kilometer between each line. The lines go vertically, half a kilometer between each line. So between 25 lines, half a kilometer, you have 12 kilometers. This is the strip. Now we have to say each of these points there, each of these points is a converter. And it's let's say you are in deep water, the ground is a couple of kilometers or so below, so you cannot actually have your fixed point for against which the converter is working put on the ground. It doesn't make sense. So you want something which the different parts were, okay? And we took a simple model. I don't say this is the best engineering solution, but as a model, what we looked at is the concept of a twin cylinder wave energy converter. And this structure about which I'll talk in the next few minutes is just one of the dots that you have seen in the farm. In the farm there can be thousands of these dots of converters, and then you have several farms over you. Okay. Now this structure, as you can see, this is the water surface. You have a floating cylinder. You have another cylinder deep, which is in neutral buoyancy. Maybe a little bit wants to sink. They are made of two different materials in the sense that they are to make their flotation stable, and this is the split that you see here. They are somewhat heavier above than below to have stable flotation. They are connected by absorbers, kind of dashpots all around, in order to be also effective. The motion that these go, if they have a wave attack, them will be heave, sway, and roll. So in order to be also more effective in roll, we put it all around. And to simplify, to not have too many parameters, which already have quite a few, we took all geometrical dimensions to be the same. The radius of this cylinder, the total depth of this cylinder, called draft of this cylinder, the spacing between both cylinders, all we took to be the same quantity Q. I don't say it's the optimal one, but we have one which we want to get a feeling how big it is. And then we also need to choose this lambda D, which will be our basic system of energy absorption. So, what is the logical procedure if you look on such a device, or how you treat it? So the twin cylinder wave energy converter, what are design considerations? Not that we really do design, but let's call it like this. As I said, for simplicity, the cylinder draft, cylinder spacing, cylinder radius will be of the same, will have the same quantity Q. The three important quantities in analyzing such a structure is K, the wave number of the, if you think about the picture of a single wave, then we go to many waves later. If a single wave attacks such a structure, so the K is the wave number of the attacking wave, Q, which is given, is the input, and the output parameters which we want to find will be the size of the structure, how big are these structures, and what is the, and we get a value for the dashpot for which we have no feeling. We don't, these are not dollars, we have no feeling. For size we have very good feeling, not for this number, but we need it anyhow. So what is the procedure? We have to choose a design wavelength. This is a different lambda. The one is lambda with D, with a dashpot. This is just a lambda. Or alternatively, you can choose an energy spectrum. For example, the lambda can be a 100-meter monochromatic wave, which you don't have in the ocean, but we can have it in our mind. Or a Pearson-Moshkevich spectrum, which has the peak, let's say, at a wavelength of 100 meters. But let's continue for the time being with a monochromatic wave. Now, we choose a device size parameter Q, which produces the largest relative displacement without damping. We solve this problem of the two waves, which in 3 degrees of motion attack the two cylinders. Each of them has 3 degrees of motion, heave, if the waves come from here, heave, sway, and roll, and using mainly method of, we take different zones there, take method of separation of variables and so on, and we solve this this problem. The first step, which appears here, is taking lambda dfs, and we are looking which Q will give us a maximum motion between these two cylinders. Then, once we have found this, we choose lambda d, the damping, to maximize the absorbed power. This I say in a few sentences. It's a lot of work. Not difficult work. It's all linear theory and so on, but it's a lot of calculations. The resulting design may then be evaluated for performance and survival in other conditions. In what follows, we consider we've taken the 10 meter per second wind as a design wind, or this 100 meter wavelength. We consider a fixed design. Q turned out to be a bit more than 10 meters. So these are big structures, diameter 20 meter, draft 100 meter each. You can calculate the volume. These are big structures, very big floating structures, but they have to capture energy from relatively big waves. Optimized for power capture of a monochromatic wave with 100 meters. So first of all, we have a feeling about the size of the structures and so on. Now, what you see here is we see on the vertical line the captured power of a single converter PA for both, in two cases. One was a single cylinder which was connected to the bottom. The other one was our twin cylinder. The act very similar. It was tuned to be very efficient at this value of k, which is the 100-meter wave. Is the wave number of the 100-meter wavelength, and this shows how the structure behaves for a variety of wave numbers. The design wave was 100 meter. Our two cylinders had a Q of 10.3. This is a lambda. We have no feeling what the number is, and this shows that we know to calculate the power absorbed by each of these cylinders. Next up is more complicated, and I'll jump on it very quickly. Now, we don't have a single cylinder. We have a big array of cylinders. But the array is made of lines. And here we assume that the spacing between the cylinders is quite big, mainly compared to the size of the cylinder. The cylinder radius is 10 meters, and we speak about distance of the order of half a kilometer. The wavelength is in between, is 100 meters. So it's in between. This allows us certain simplifications. Not completely rigorous, but very practical and useful, by which we can analyze. Sorry about that again. Where I have to go back. Here I was, no? No. I want to go back. Here I was. We have to analyze the behavior first of a single line. In the single line, you can analyze both in normal incidence and in oblique incidence. We have done that. And I skip the details. The details are given here. I mean, the results are given here. What you see here is the energy transfer function for normal incidence. You have the blue line is the power absorption divided by the incoming power incoming power of the wave field. You have the transmission, the green line. The power absorption, sorry, is the green line, and the blue line is the energetic reflection coefficient. How much power from the power that comes is reflected. You can also calculate what is transmitted. And then what is transmitted comes to the second line and so on. And you have to calculate it over the whole width of this farm. So this calculation was repeated for oblique incidence. And just to give you an overall picture, what you have here, you have a schematic depiction of the array at macro scale left, where you see the lines, where you can see the lines of the absorbers. The individual absorbers you can see more in detail in the center, and then to the right you can see a single absorber. And we have to integrate all this. Here you have the formulas which give you the relation between what is done by one line, by the second line, and eventually by n lines of absorbers, both in respect to the energy transmitted. Actually, turns out the transmission of a coefficient for n lines is just one. The transmission coefficient for one line to the power n, whereas the captured power goes down by this geometric series, and you have an expression for the total power which is captured over this structure. And I skip this because of shortness of time. We can now calculate the, just say very briefly, the green line gives us the absorption. You see the maximum absorption is about, absorption coefficient is about 40%. The reflection is also about close to 40% at the best performance. We assume that waves that move against the wind will eventually die out. Some way to make this assumption. And we also have the energy which is transmitted to the right from the waveform. Now this enables us to make much more accurate calculations than we did with the ideal model, of course. Now we have real structures which we put in real waveforms and have a relatively good assessment of the numbers. Just to show you a picture what the farm is going to do, a single farm, if the wave spectrum, the two-dimensional wave spectrum of the wave field before it enters the farm looks like this, after it goes out from the farm is taking quite a bit of energy out of it. It looks like that. Actually, if you work out for a single number, the eighth significant, which was before the farm, which was about 2.5 meters, goes down to a little bit below 2 meters when it goes out of these 25 lines. Not zero, guys. It doesn't work like this. Now, what happens? Wind blows again. And wind works to regrow what is here to more or less this shape. And where this happens, we put the next farm. So array dimensions and spacing in a 2,000 kilometer long basin. We have given the same design wind of 10 meters per second, and we know that x0 has to be larger than the fully developed fetch. It must be larger than about 350 kilometers. We have to determine both the number of lines, what will be optimal. I spoke about 25, but maybe you want 10, maybe you want 50. What's the optimal number of lines? And then this will affect also the number of farms. So even with these simple parameters, you have many very specific questions. All this, of course, based on the regrowth of the waves between the farms. Because of the shortness of time, I will skip the various considerations, and I go to the harvesting wave power in an ocean basin. The greatest overall power for a design wind of 10 meters per second will be in a farm which is 10 lines, not the 25 that we just chose out of the sleeve earlier. 25 lines per farm. The leading fetch will be 371 kilometers. The first farm will catch this amount of power per meter. It will catch about 10% of what will be caught eventually. Inter-farm spacing will be about 58 kilometers for regrowth of wave field, and the total farms which we'll have will be 27 farms. So we'll have 27 farms in this stretch of 2,000 kilometers. The overall capture over all these farms will be almost 50 kilowatt per meter. You have many meters. You have about 100 kilometers, so you have 100,000 meters there. Harvesting wave power in open ocean. Now for two-dimensional waves comparison of farms with varying winds. Okay, I won't go over the details, but we have to check how good is such. Because we had a design wind speed, but in nature you have various wind speeds. So how it works in smaller wind speed, how it works on larger wind speed, and we don't have enough time. I won't go into the details on this slide. And we have some discussion of what we have seen, or kind of maybe it's kind of very close to it. It's actually a summary. From a simple picture of wave growth by the wind and an ideal absorber, we understand that moving offshore increases the potential to capture wave power fivefold. This is what we have seen from the ideal, which was very easy to calculate. A wave energy converter based on a relative motion of twin coaxial cylinders was developed as an illustrative point absorber. This WEC may be tuned to a spectral peak and its behavior in various sea states examined. So we have the full solution of the hydrodynamic linearized problem. Taking sparse lines of such WECs allow the derivation of the power transfer functions, the power absorbed compared to the power income, and the energetic reflection and transmission coefficients. The behavior of large arrays of twin cylinder WECs made up of many such lines is analyzed macroscopically for both normal and oblique incidents. One array, 10 lives deep, captures about 10% of the incident energy flux under design conditions. Over the course of this 2,000 kilometer basin, the advantage of multiple capture grows to 25 times that of a single coastal farm. So if you would take the same conditions and just have a single coastal farm, the way that it's not a simple thing to put all these things out in the ocean, but our mind, we can do this. We can increase the capture 25-fold that one. And this is the main thing what we wanted to see, that if you want to catch really nice quantities of energy from the ocean, eventually you have to go out. So if you're happy with smaller quantities, you can stay near the coast. There are a lot of details which I was not able to discuss, of course, in this 1 hour talk. And the group, Dr. Chu, Dr. Stuhlmeier, with a little bit my contribution. We also had another colleague who worked with us, which is Dr. Usama Kadri, now at the Mathematics Department of the University of Cardiff. Is published in a series of papers. We developed it rather slowly. We also looked, and I skipped that, but I just tell you that we looked what happens with these structures at very severe conditions. When you have a wind not of 10 meters per second or 12.5, but of 20 meters per second. And I don't remember what is the wave height, but it can be 6 meter high waves. Are they surviving or not? It's a question. And consideration of survivability indicate, and this is just one thing which I'll say, that we will probably not go with the about 10 meter diameter, but will increase the due to reasons of survivability and so on. We'll have to increase the size to size G, which was 11.5 meters. This will survive what are the allowed motions and so on. You have to, okay, so more or less I come to an end here. And this is just, I finished that project and I'm starting a complete new project. If you know, which is not in linear theory, I usually make my living not from linear theory, but from nonlinear theory. I said be wise, linearize, but some people say linearity breeds contempt. So you have both aspects of the problem. I'm starting a new project on forecasting of a freak wave based on extensions of Albert's equation. Albert's equation is a stochastic relative of the cubic Schrödinger equation. Some preliminary work on this has been done by me and other people, appears in a couple of papers in Journal of Fluid Mechanics. But we are now substantially going into a much broader picture, and I'm looking for a good postdoc. If you have somebody who's looking, wants to come to Israel, enjoy the sun, he can talk also with Raphael Stuhlmeier. He will tell him if it's good or bad. So thank you very much for your patience.
Okay, questions?
Very clear the talk.
Okay, I'll ask a question. When you, I think this is about slide 12. Might be easier to refer to that.
Want to go to slide 12?
I think it's 12 out of 20.
I'll try to go to 12.
Okay, line number 2. You said,
Item number 2.
yes, choose device size parameter Q to produce largest relative displacements without damping. How large were those displacements?
I beg your pardon?
How large were those displacements?
How large they could be on about the size of a Q or half Q or something like this.
Okay. Did you think of detuning rather than looking for resonance?
You say think about
Detuning.
how
You optimize across the spectrum using the design parameters.
we use this approach which we have more or less adopted from a series of papers by May and co-workers. But we have not used the approach that I don't know if you get a different end result.
The problem with your method is that if you have a very big spectrum, it's fine. But if you have a broad spectrum, you'll lose bandwidth.
It's not efficient. You get no, absolutely right.
That's what you have to change the parameters. You have to do it to match your spectrum.
You want a system which you tune according to the waves.
I do.
So like you change the dashpot or something like this.
Well,
yeah.
there are two stages. The first is design, and once you've built it, you can't change it.
Okay.
But you can change the power takeoff.
This one. That's all.
So you need to look at all of those with regard to the spectra that you're going to use, and that will give you a good
More efficient.
much more.
Will it be more efficient in a wide range of spectra and so on?
Yes, and it'll also keep your displacements down.
Okay, we have not done that. Thank you very much.
Thanks, Becky.